Number 7, evaluate the integral x squared times the quantity x cubed plus 5 to the 6th power. All right, so since there are parentheses on this one, we know we're going to do a u substitution. So u will equal what's inside of the parentheses, which will be x cubed plus 5. My du, my derivative of x cubed plus 5, will be 3x squared dx. I notice that I have x squared and dx in the problem. I'm just missing a 3. So 3 on the inside, 1/3 on the outside. So I now have 1/3. And let's just evaluate what we have. We called this u, and the 3x squared dx we called du. So now I have u to the 6th du. So I'm going to bring down my 1/3 because it's a constant, and then the integral of u to the 6th will raise the power by 1, so we'll get u to the 7th times the reciprocal on the outside. So this will be 1/21 u, which is x cubed plus 5 raised to the 7th power, plus c. Okay, number 8, evaluate the integral, the tangent to the 4th x secant squared x dx. Again, I'm going to do a u substitution, and if you know your derivatives, this should be an easy one to pick. I'm going to let my u be the one that has the highest power, so without the power, so I'm just going to let u equal the tangent of x. Du, the derivative of tangent, is secant squared x dx, and I notice that is sitting right in my problem, so I'm all set to go. So we called the tangent u, and secant squared x dx is my du. The only thing that I have not used is that 4th power, so now I have u to the 4 du. And then from here, the integral of u to the 4, we'll just increase our power by 1 and make it u to the 5th, and then the reciprocal of 5 would be 1/5. So now we have 1/5, my u, which was tangent, it's going to be raised to the 5th power now, plus c. Okay, number 9, we want to evaluate the integral from 0 to pi over 2 of 6 sine x square root of cosine x. Since we have a square root in our problem, we're going to let u be what is inside of the square root, so we'll let u equal cosine x. So du will equal negative sine x dx. Probably a couple things we could have done here. I think because 6 is a constant, I'm just going to bump it out front to start with so I don't have to worry about it. We could have done a different approach, which would have been fine as well. So du is negative sine x. I'm just missing the negative on the inside, so a negative will go on the outside. So let's write down what we now have. So we now have our u, this was our u right here. The sine x and the dx were du. And notice I have done nothing with the square root, so we still have the square root of u du. And I'm going to rewrite that as negative 6, the integral of u to the 1/2 du. I'm also going to do one other thing here. I'm going to go ahead and change my limits. Just, I think it's an easier problem. I'll do it without changing the limits as well. So when x equals pi over 2, u is going to equal the cosine of pi over 2, which will equal 0. And then when x equals 0, u will equal the cosine of 0, which is 1. So if I change my limits 0 to pi over 2 to 1 to 0 for both of those, notice I cannot go 1 to 0, so I'm actually going to take the opposite of that. So instead of being negative 6, it's going to be positive 6, the integral from 0 to 1 of u to the 1/2 du. Okay, and now I'm just going to evaluate it here. I'll have 6 times u to the 1/2. If I add 1 to that power, I'll get u to the 3/2 times the reciprocal on the outside, which is going to be 2/3. On the outside here, that's going to reduce to 4u to the 3/2. And now I can just plug in 1 and plug in 0. So I'll have 4 times 1 to the 3/2 minus 4 times 0 to the 3/2. And 1 to the 3/2, the square root of 1 is 1. 1 to the 3rd power is 1 times 4 is 4. Minus 0 to any power is just 0. So that's just going to be 0. So my answer is going to be 4. Okay, I am going to work this if I did not change my limits, just in case you don't care to do that. So we would have still had 4u to the 3/2, and then I would have just plugged my u back in, so that would have been cosine x to the 3/2. We would have just evaluated at pi over 2 and 0. So I would have had 4 times the quantity cosine pi over 2 to the 3/2 minus 4 cosine 0. Wait, I would have had a negative out there, actually. So this negative would not have gone away had I done that. So this technically would be a negative. So it would be negative 4 cosine of 0 to the 3/2. So that would turn to plus. Okay, so cosine of pi over 2 is 0. So this whole part's just going to be 0. And this is going to be 4 times the cosine of 0 is 1. 1 to the 3 halves is 1. Times 4 is, well, that would have been times 1. Okay, so my final answer would have been 4. So either way is fine. I think this way is a little bit easier maybe, but totally up to you which way you would like to approach it. Okay, the integral evaluate from 0 to 3 of 1 over 2x plus 1 dx. Once again, we're ready for a u substitution on this one, so we're going to let u be the denominator. So u will equal 2x plus 1, du will equal 2. And then I notice I only have a 1 here, so I need a 2 on the inside, which means I'm going to put a 1/2 on the outside. So I'm going to have a 1/2 on the outside. Let's just evaluate what we have here. The 2x plus 1 we let be our u. The 2 dx we let be our du. Okay, so on the top we have the du, on the bottom we have u. Okay, and from here, again, I am going to work it 2 different ways. This one I'm going to go ahead and find my values for u. So when x equals 3, u will equal 2 times 3 plus 1, which will be 7. And when x equals 0, u will equal 2 times 0 plus 1, which will be 1. So this is going to go from 1 to 7. So then when I go ahead and evaluate my integral, the integral of 1/2 is just another 1/2. The integral of du over u is ln of the absolute value of u. And now from here, I don't need to replace. I can just put my 7 and my 1 in. So here I'll have 1/2 the ln. The absolute value of 7 is just 7 minus 1/2 ln. The absolute value of 1 is 1. The natural log of 1 is 0. So my answer will be 1/2 ln 7. Okay. Had I not switched my variables, we would have had 1/2 ln of u. I would have replaced my u back with the 2x plus 1, and then I'm just going to evaluate it at the 0 and 3. You'll notice when I evaluate it at 3, plug the 3 in. 2 times 3 is 6, plus 1 is 7. The absolute value of 7 is 7. And then minus 1/2 the natural log. If I plug 0 in, 2 times 0 is 0, plus 1 is 1. The absolute value of 1 is 1. And once again, the ln 0 cancels out. So notice you get the same answer either way. You can decide which way works best for you. Okay, number 11, evaluate the secant of 8x. So I see parentheses, so I'm just going to let my u be 8x, which means my du, the derivative of 8x, would be 8 dx. I am missing an 8 on the inside, so 1/8 on the outside. So let's just evaluate what we have. We let the 8x be our u, and the 8 dx became our du. Notice we have not done anything with secant yet, so secant is still in my problem. So this will be secant u du. And hopefully for this problem you know your trig integrals, because I do, so I'll be able to finish the problem. So I'm going to have 1/8. The integral of secant u is natural log secant u plus tangent u. And now I'll just replace my u and u's in there. So I'm going to have secant 8x plus tangent 8x plus c. Number 12, evaluate the integral of 4x minus 6 over x squared minus 3x plus 5 dx. This is going to be another u substitution where we will let u be the denominator. So we'll let u equal x squared minus 3x plus 5. Our du, the derivative of x squared minus 3x plus 5, will be 2x minus 3 dx. And I notice that we have 4x minus 6 in the numerator. If I multiplied that expression by 1/2, I would have 2x minus 3. So I'm going to multiply the inside by 1/2, which means I multiply the outside by 2. So let's evaluate what we have now. So I have 2, the integral. We called the denominator u, and everything in the numerator is going to become du. So now we have du over u, and we know that if we have du over u, it's a natural log, so it's going to be 2 natural log of the absolute value of u. And now we just get to put our u back in. So we'll get x squared minus 3x plus 5, and then, of course, plus c. All right, number 13, evaluate the integral of e to the 3x over the square root of e to the 3x plus 4. We learned that if there is more than one e in the problem, we are going to let e be a chunk. And the chunk that I'm going to let it be is the e to the 3x plus 4. I'm going to ignore the square root for right now. So u will equal e to the 3x plus 4. And then my du, my derivative of e to the 3x plus 4, will be 3 e to the 3x dx. All right, I notice up top I have e to the 3x, but I'm missing a 3. So I'll put a 1/3 on the outside. So again, let's just take stock of what we have here. Notice we called inside of that square root the u, and everything in the numerator became du. So I have du over, we have not done anything with the square root, so the square root is still there. This is not an ln problem because it's not just u down there. So I'm going to rewrite this as 1/3 u to the negative 1/2 du. And now I can use my power rule to actually evaluate this. So I'm going to have 1/3. If I increase my power by 1, I'm going to have u to the 1/2 times the reciprocal on the outside, which will be 2. So now I'll have 2/3 u to the 1/2. So that will be 2/3 u to the 1/2 is just a square root of my u, which was e to the 3x plus 4, and then plus c.